Our DMF project is going to be done on the biological microscope. This is for the MFG 452/ISD 528 Advanced Design for Manufacturing for Winter 2024. As you can see, our assembly CAD model, this is our biological microscope, and as you can see, it has 24 total parts, and we'll get into a little bit of those lenses and things like that in the further slides. This is our CAD model as well as our assembly. And then in the next slide, you'll see our exploded CAD view. Now this shows all of the parts exploded so that you can see how they all interact with each other, and as well as like the different threading and things like that. As you can see, a lot of different parts here, and we'll get into which one of those in later slides that we are going to have for our different family groups.
Two target customers are students and professionals. The students ranging from middle school to university might have little knowledge of using the product with limited exposure. On the other hand, professionals might have high knowledge in using the product with more than 200 hours in total. The production volume is expected to be around 50,000 per year. Let's talk about FAST diagram. The main purpose of the microscope is to magnify specimen, followed by stabilizing slide, adjusting focus, assuring dependability, assuring convenience, pleasing senses, and enhancing product. Left to right, it explains how to use the product. Right to left, it explains why. The FAST diagram is shown below.
The following slides display two possible assembly sequences. The fishbone diagrams of both assembly sequences flow from the left to the right as components are added to the final assembly. This is the first assembly sequence. This sequence focuses more on grouping parts into subassemblies. These subassemblies are pre-assembled before being incorporated into the final assembly. This is the second assembly sequence the team discussed. This sequence is a bottom-up approach which follows a vertical assembly path starting with the base and ending with the eyepiece. After discussing the two sequences, the team developed this comparison table, with a scale ranging from 1 being low to 3 being high. Assembly sequence 1 is the better strategy due to the use of better defined subassemblies, allowing for easier parallel assembly and a later lens differentiation.
In creating a bill of materials for a biological microscope, we opted to purchase standard parts such as fasteners, as well as complicated components like the lenses, while manufacturing all other parts. The cost of the purchased parts was determined based on similar or identical parts which could be purchased in bulk from hardware wholesalers. The material, processing, and tooling costs for the manufactured parts were determined from estimates provided by CustomPartNet.com. The total cost of each component is colorized at the far right. The parts which were determined to have low functional importance, such as the standard fasteners, should be eliminated from future designs. The parts that have high functional importance and low total cost will only be slightly modified. The best candidates for improvements in future design iterations are shown in the black lower right quadrant. These parts are both functionally important and expensive to manufacture.
Here we have our functional component mapping matrix, which lays out the components from our fishbone diagram with their functions from our FAST diagram. As you can see, the adjust height and align eye functions are the most widely distributed across many of our components. This holds some inefficiencies due to the spread of these functions across so many components and warrants a possible redesign. Additionally, our customized magnification function is our primary variant, which we will break our families into, and is driven mainly by our nose piece and lenses components. As previously discussed in our functional component mapping matrix, our customized magnification function is what will differ in our differences for the variants and drive our module selection.
The component commonality table shows the major components of the microscope and whether they are common platform parts or specific to the module. The current design utilizes different lenses based on customer use cases and the carrier or nose piece component in which those lenses are attached. This part sharing strategy minimizes differential part count while meeting both customer base needs. Two variants of the microscope are shown to illustrate the common interfaces of the design. The 3-lens and 5-lens variant use common interfaces to the optical structure while changing the number of lenses and types of lenses between the two identified customer bases. Two sequences shown here in the product family assembly diagram both show valid assembly sequences. However, the first sequence delays differentiation of the assembly until the last step where the nosepiece is added. The second sequence subassembles the nosepiece as part of the eyepiece, and then requires earlier assembly differentiation.
Thank you for listening, and we look forward to your comments and feedback.